Okay, so good morning, everybody. So, so maybe I'll just start with a little brief recapitulation of what I talked last time. So last time, the lecture 1 was basically an overview of random matrix theory. So people at the back, can you see, if you don't see it well, just let me know, okay? And I'll try to write, because when you write, you know, naturally it gets smaller. And so you, I mean, but yesterday I was sitting at the back and I couldn't see many, some of the things, so just tell me, okay? So I started with an overview of random matrix theory. And so the main thing, I told you the main program was that you had an n by n matrix. Let's say with elements x11, x12, etc. And the elements of these entries of this matrix are random variables. And in general, they are drawn from some joint distribution of the matrix elements. And we'll be more specific today about the particular type of matrices that we'll be talking about. But in the most general setting is that you have a random matrix with entries which are drawn from a joint probability density function, which is denoted by P of xij. Yes? No, because the elements could be, I mean, as we'll see many examples, elements could be that they are correlated, okay? There are some examples where they are correlated, okay? So, or, I mean, so most general setting, I mean, you know, if they are independent, that's a particular special case of this. When these things becomes factorized of, you know, when they are independent, it just factorized into individual distributions, okay? But this is a more general setting. So I'm talking about the most general setting right now, okay? So you have the joint distribution of these matrix entries, and then there are two steps from this. So the step 1, which is often very non-trivial, is that, so for each realization of the matrix, you diagonalize this matrix, and you get the eigenvalues and eigenvectors, and then you integrate over the eigenvectors, and to derive the joint distribution of eigenvalues. We'll see some specific examples. This is just most general setting I was talking about. So we'll get the joint distribution. So this is the first step is often quite difficult, okay? And once you have this joint distribution explicitly, then the second step is to, starting from there, you analyze, you treat them like a statistical mechanical system, okay? So this is like positions of some charged particles, we'll see that precisely. And then you want to calculate, compute some observables, statistical properties of these observables. For example, one thing that I talked about last time is the spacing distribution between eigenvalues, or you can ask about the overall density of eigenvalues, or you can ask about, I don't know, other things, for example, distribution. So there is a lot of current interest which is regarding the distribution of the largest eigenvalue, okay? So one example is the largest eigenvalue. How is the largest eigenvalue distributed? So this is the lambda max, which means maximum of all the eigenvalues, maximum or minimum if you like, that is the minimum eigenvalue. Because if you are a disordered system, you see the lowest eigenvalue will be like the ground state energy of the system, okay? And so there is a lot of interest in this top eigenvalue of the random matrix, top or bottom if you like, by symmetry often they are same. And so there is almost a kind of revolution in both statistical physics as well as in probability theory. Over the last few years, like 20, I'll say 10 to 20 years, where this distribution of this lambda max was calculated for Gaussian random matrices by two mathematicians called Tracy and Widom in 1994. So in the beginning, they just computed the distribution, and so then the problem stayed for a while, and then it turned out later that somehow the same distribution of the lambda max for Gaussian random matrices appeared in a huge number of problems, both in statistical physics and probability. And in fact, there is a close link, more recent work, till 2010 or something, that it turned out that this is also closely related to non-equilibrium statistical physics that Kiran has been talking about, namely the asymmetric exclusion process, or what is called the interface fluctuation models like Kardar-Parisi-Zhang equation, which is actually the same thing, I mean in different language. Okay. KPZ type. KPZ stands for Kardar-Parisi and Zhang. Okay. So this distribution which appears in random matrix theory also appears in this set of problems in non-equilibrium statistical physics. So there is a lot of development and lot of work which has been happening now, and there are a lot of new experiments, okay, which is also another interesting point. And now there are experiments to measure this distribution here, okay. And so this is the sort of more modern development which has happened over the last few years, and I'll try to sort of cover some of it as much as I can during the course of my lectures, okay. So just remember this chart here. So there is the first step, which is basically mathematics, okay, and then the second step, which is more like statistical mechanics. So one second step is that knowing the joint distribution, you want to calculate some observables. And as I said, this is exactly like what I talked about yesterday, and Kiran was also talking about it. That is, like in the Gibbs distribution, you know the measure, okay. But knowing the measure, like in Ising model, you know the probability distribution of a configuration of spins. So in the Ising model, these are spins, for example. But to calculate from that the free energy or magnetization, etc., is a formidably difficult problem. I mean, as you saw 2D Ising model, Onseger solved this case for zero magnetic field. Even then, it was a very difficult problem. So this second step also is a difficult problem, but this is more in the domain of combinatorics or statistical physics, basically. Okay, and so there are many observables. I mean, as I said, spacing distribution, then so the density of states. So I'll define all these things as I go along. Distribution of largest eigenvalue, etc., etc. Okay. So there are many other different questions, and these questions actually naturally appear in random matrix theory, and also depending on which application you are talking about. So those applications actually ask different questions, and so so it's a very useful thing, because I mean, once you know this, then you can ask. So for example, analog of magnetization would be just the trace of summation lambda I. What is the distribution of the trace of lambda i's, and things like that. So it depends on the questions that you're asking, but basic program is that given this, so this is equilibrium statistical mechanics, if you like. You give me the joint distribution, that is the stationary measure of this, and in thinking of this as degrees of freedom of a statistical mechanical system, I want to calculate the observable properties. Okay. So the overall program of my talk would be to start from here. So we'll start from this, and we'll first see in some simple examples how to calculate this joint distribution, starting from the entries, and then from this, then we'll try to go there and try to calculate some of these objects, and then finally I'll talk about the largest eigenvalue and the recent developments. Okay, so that's the sort of program or outline of my talk. Okay, so let me today start just with. So today's thing would be to start from this and come there. I don't know if I can complete this step, but we'll see how much you can do. Start from the joint probability distribution of this, and as I do, I mean, a la Wigner, it's always useful to keep in mind the 2 by 2 example. Okay. So in fact, I mean, if you understand what is going on in 2 by 2, it's not that difficult to generalize to n by n matrices. Okay. So we want to define. So basically, we are taking these as random variables drawn from some joint distribution. So when we say joint distribution, so this is the probability density. That means actually what you want to write down is something like this. So you have all these random variables, and then you have this measure, which is dx11, dx12, etc. And you have to specify what is this object here, and this is just the elements number of independent degrees of freedom. Now, before I go on to define the measure and probability distribution, what I'd like to do today is to start reminding you some very basic properties of matrices, or most of you know it, but it's actually useful to do that so that we know what we are, the notations are clear and so on. Okay, so let me do that first. So, reminder of just matrices, okay? Forget about random matrix, just ordinary matrices, okay? Given matrix, some matrix properties. Okay, so suppose X, I'll always denote by capital X as my matrix, Xij. So this is an n cross n matrix. So as I said, in general, if there is no symmetry in the problem, the eigenvalues of these matrices are going to be complex. Okay? So not all matrices have real spectrum. You can of course study the matrices with the complex eigenvalues, but because originally it came from nuclear physics where this was supposed to be the Hamiltonian. So for Hamiltonian, you know that the eigenvalues are real. So physicists were more interested in matrices with real spectra. That is, those matrices which have all eigenvalues real. Now, what could be such matrices? So what type of matrices? So if I give you a matrix, what are the properties that you need, okay, for it to have real spectrum? So there's one very simple example. Can any of you tell me just one type of matrix which has real spectrum? Sorry, Hermitian matrices, very good. Okay, even simpler, if I take a real symmetric matrix. Which means that Xij's are real and Xij is same as Xji. Okay? Just a real symmetric matrix. So this has real spectrum. Then, as you said, second example is complex Hermitian matrices. So complex Hermitian matrices, Xij's are complex numbers, and basically you have Xij star is same as Xji. Okay, so that means X dagger, which means X transpose star, is same as X. So complex Hermitian matrices. So this is the thing, for example, if this is a Hamiltonian of a system. This could also be a Hamiltonian of a system in absence of time reversal symmetry. So, for example, if you do not have any magnetic field in the system, often you can actually have eigenvalues, I mean, even the matrix elements which are real. You can choose a basis in which matrix elements are real. Okay. There is yet a third class which is not so well known, probably. I mean, some of you know maybe, which is called the quaternion self-dual matrices. So how many of you have heard of quaternion? Has anybody heard? You have heard. Only one person, two, three, okay. So there are quite a few. So okay, I can define quaternion matrices and tell you a little bit about it, but maybe that will take me away a little bit from the main development of the course. So maybe in the tutorial we can discuss. So we'll discuss. So this is another type of matrices you have to know, which are, I mean, quaternions are just generalization of complex numbers, okay. So complex number, any complex number, you write as a plus bi, right? So a and b are real, and I is just the complex root of -1. So here you have I squared equal to -1. Okay? So this is the complex number. So quaternion, so it has two bases here. Quaternions, if I write a Q, quaternions are numbers which are generalization of ordinary complex numbers. So you write down like this. So I, J, K are objects which satisfies this algebra. I always forget this. Oops. Okay. So this is the algebra. So it's a base of 4, okay? And I, J, K are just satisfy this algebra. So this is just a generalization of complex numbers. And you can construct matrices with quaternion elements in it. And okay, I can discuss this in detail. And then if you choose some self-dual properties, which I'm not defining here for the moment, so this also has real spectrum. And these are useful when in some problems, in some Hamiltonians, which where you don't have where you have spin orbit scattering and things like that, which does not conserve the total spin. So in that case, the correct basis is the quaternion basis, okay, elements. So anyway, let's not stop, go into the details of this. This will be a dry mathematics. So you can do. So this was discovered by Hamilton in 1836. Okay. So these three types of matrices are guaranteed to have real spectrum. And these are called, these three ensembles, I mean, they are called Dyson's threefold way. I'll talk about only trivial things, okay. So this means that if it is real symmetric, that means X transpose is same as X. Okay? So all the eigenvalues are real. So this matrix can be diagonalized by an orthogonal transformation. So if I take this matrix X, oops. Different people use different notations, but here, so lambda is this diagonal matrices. And this matrix O here is a orthogonal matrix, meaning that O transpose, this is a n by n orthogonal matrix. O transpose O is same as O transpose, which is the identity matrix. So which means O transpose is the same as O inverse. So this matrix O, I mean, this is just, class 10, not class 10, maybe BSc physics that you learned. So and you recall that the columns of this matrix, okay, these elements, these are the eigenvectors. Okay. which are orthonormal. Okay. So those of you who have forgotten the basic matrix analysis, just try out this simple example, always 2 by 2. Okay. So for example, here there's 2 eigenvalues. This is really, extremely trivial stuff, but it's always good to remind you. Okay. So 2 eigenvalues you can determine from the characteristic equation, which says 1 minus lambda minus 1 equal to 0. So this gives 2 roots. So lambda equal to 0 and 2. And the corresponding eigenvectors for lambda equal to 0 is 1 over root 2 minus 1 over root 2. And lambda equal to 1 is 1 over root 2, lambda equal to 2, sorry, 1 over minus root 2. Okay, so these are orthonormal. So therefore, the matrix O, which is just this guy, take out 1 over root 2 here, 1 minus 1, 1, 1. Okay. And you can check, of course, that O transpose XO gives you diagonal matrix, which is 0, 0, 0, 0, 2. Okay? Just to remind you, always do the, and similarly, complex Hermitian matrix, transpose, and then complex conjugation of that. Okay? So once again, you have all the eigenvalues are real, and this matrix can be diagonalized by an unitary transformation. So there will be U, I think, U dagger if you like. Where so U is now an unitary matrix, which is the definition here. And once again, the diagonal matrix will be like that, and the matrix U will be similarly, it will be an n by n unitary matrix whose columns will be the eigenvectors of this X matrix. So just check, for example, if you take the matrix like X equal to, just a simple example, 2 by 2. This is the trivial exercise if you have forgotten. And so here you can check that the unitary matrix will be 1 over root 2, 1i, 1 minus I. And the eigenvalues are, again, 0 and 2. Okay. And similarly, you can do for the quaternion matrices, which I am not going to do because it's not that difficult, but it just takes more time. Okay, so this is trivial exercise. So now we want to go back to random matrices. So again, I have this matrix X, which could be any of the 3 classes there. Okay, but think of always real symmetric matrix. Other things are easily generalizable, etc. Okay, so here you have the symmetry that Xij equal to Xji. Okay, so real symmetric matrix. Now I want to make them random, but always keeping this symmetry here. Okay, so that means I want to define some joint distribution of these matrix elements. But notice that because of this symmetry, how many independent variables you have. Because of the symmetry, these elements here on the left diagonal block will be same as this one, except for the diagonal elements. So how many independent degrees of freedom for n by n matrices? If I want to keep this symmetry, then I can choose independently only the upper diagonal block here, right? So how many are there? Anybody? Okay. So this is just, exactly, that's a good answer. So this means I have to just add 1 plus 2, start from the corner, 1 plus 2 plus 3 up to n. So this is n into n plus 1 over 2. Okay. So when I define this joint distribution of the elements, so here my independent elements are x11, x12, x13. So for example, for 2 by 2, again keep the example of 2 by 2 in mind. So this is x12 because of the symmetry, and x22. So there are 3 independent elements. So I have to define x11, x12, and in this example x22. And then I have to define here dx11, dx12, dx22. Okay? So I don't have the dx21, remember. Okay? So this is the measure. Now, this measure, before I go on to this P, let me just make some comment on this. Okay? It's somewhat non-trivial. Okay, so what is the comment I want to make? All of you know the following things. Okay, again, this is very basic, but you have to keep reminding yourself. So imagine that I have a vector, okay, in the real these things, space, 2-dimensional space, so 2 by 2 matrix. So I have a vector, eigenvector, let's say. So let's say this is the vector, I don't know, you call it x. So you make an orthogonal transformation. So I have a vector x, which I'll denote by these 2 components, let's say x1 and x2. Okay. And suppose I rotate this vector by an angle, okay, and I go to x prime. So this x prime vector, its elements are x1 prime, x2 prime, right? So this is an orthogonal transformation. So that means this vector x1 prime, x2 prime is related to x1 and x2 by this transformation. So this is an orthogonal matrix O. So O relates x prime, this vector, as O times x. Okay. And what is this vector here? Anybody? Cos theta, then minus sin theta. Huh? Okay. Very good. So this is the orthogonal rotation, which keeps the the vector, the magnitude of the vector to be same, preserved. Okay. So here now, if I take a volume element here, okay. So what you want to show is that suppose I take dx1 prime, dx2 prime. Okay. So this is, all of you know this. This is a Jacobian times dx1 dx2. So what is the value of this Jacobian? Anybody? All you have to do is to take del x1. The Jacobian is just this matrix, and this determinant of this matrix is what? 1. So this Jacobian is 1. Okay. That means if I have a volume element here, dx1 dx2, it remains preserved. dx1 prime, dx2 prime is same as d1 dx1 dx2. Okay. So that's very simple. It's always true. So if I take a vector and make an orthogonal transformation, the measure remains invariant. Okay. Now, suppose I want to do it to this one. So I have this matrix X, okay, and I want to make an orthogonal transformation. That means I multiply it by OT times O, and I get a new matrix Y, which also is real symmetric because this is the orthogonal transformation. Now, so the question is here. So let's again think of 2 by 2 example, okay. So D11, so new matrix, so Y, so this is X. So the matrix Y will be Y11, Y12, Y12, Y22. This is also symmetric. So the new measure of this matrix will be dy1 dy12, dy22. Okay. Now, question. Is it the same as dx11, dx12, dx22? This is no longer a vector. This is a matrix elements. Okay. I make this orthogonal transformation. Is this true? Anybody wants to guess? Huh? Yeah, depends on Jacobian. Do you know? Do you know what the Jacobian would be? Okay, let me work this out. So this is non-trivial. Okay, it's not. So, I mean, okay. So let me do the 2 by 2 case, and then I'll leave it as an exercise. The general n by n case. So the answer is yes. This is 1. This is true. But the proof is much more non-trivial than this guy here. So let me just do the 2 by 2 proof, which you can do by hand, or just by brute force. Okay. So what is y? So it's just a rotation by 2 by 2 matrix. So O transpose, we know what the O matrix is. This is just this guy. So O transpose will be, okay, so we said y is O transpose. Okay, so O transpose will be cosine theta, sine theta, right? So this is the O transpose. And then I have this matrix x11, x12, x12, x22. And then I have cosine theta minus sine theta, cosine theta. All right? So this is our new matrix, y11, y12, y12, y22. So let's just, brute force multiplication. I mean, you don't need to do this way. There's a much more elegant way of doing it. But I mean, I prefer to do it algebraic way, so that once you have done it, you know it, then you can always find a better method to do it. Because when you work out the 2 by 2 example, you actually see what is happening. Okay, so it's always useful to do that. Okay, so that's it. So from this, you want to calculate the Jacobian. So the Jacobian, by definition, is sorry, I'm just doing a little bit of algebra here, but I think it's just to demonstrate to you something. Some things in matrices are not that trivial. And similarly, the third element here, I'm not going to write down this. So if you just work it out from this, is trivial. So you will actually get this matrix, cosine square theta, sine square theta, 2 cos theta sine theta. Then you have sine square theta, cosine square theta, minus 2 cos theta sine theta. And the last element is minus cos theta sine theta, cos theta sine theta, and cos square theta minus sine square theta. So that's the Jacobian. So I mean, you just add these two row up, then this becomes 1, 1, 0. And then it's just a 2 by 2 determinant, and you can just work it out, and you find that this is 1. Okay. So the point is that the measure, probability measure, remains invariant for real symmetric matrices under an orthonormal transformation. Okay, so now here is the exercise. Yeah. Can you speak out a little bit loudly? Yes. Yeah, I mean, that depends on how you, I mean, I have written that way, y11, y22, y12, okay? Yeah, same thing, because Jacobi, it doesn't matter how you label the vectors, basically, okay? So here is the exercise. Prove this for general n. So of course, I don't expect you to do, by hand write down n by n matrix and do it, but this is a non-trivial proof, okay? So think about it and tell me by the end of this lectures the proof of it. Okay, so, but we'll take that for granted. Similarly, and this also I'll leave an exercise. Similarly, for Hermitian matrices, so if now I'm in Hermitian matrices, so now these are just complex numbers. Okay, so let's just work it out for the Hermitian matrices something. So in the case of complex Hermitian matrix, so for example, if I take a 2 by 2 matrix, or in general, let's say 3 by 3 matrix, so here you will x12 plus, let's say, I don't know, I write it this way, so these are real numbers. Here it will be x12 minus I, y12, x22. So diagonal elements are always real for Hermitian matrices. Okay. So for such matrices, so for example here, how many independent entries are there? So I have 1, 2, 3, 4, 5, 6, 7, 8, 9. So if I have to write a measure, I have to write as dx11, dx12, dy12, dx13. So for each real part and imaginary part, I have to, it's like exactly the way Shumit was doing yesterday when he was doing functional integral. Okay. So now if you have an n by n Hermitian matrix, somebody please tell me how many independent entries? Yes? Easy, count. Huh? Same? No, how can it be same? Because you have these guys here. Imaginary part, huh? N square, very good. So please check that these are n square entries. Okay? Basically, it's what is n square? It's just 2 times 1 plus 2 plus 3 up to n minus 1 plus n. Plus n is for the diagonal, because diagonal guys you have n, and all the off-diagonal guys you have 2 times whatever the total number of off-diagonal elements. So this is actually n square. Okay. So you have this n, so this is the measure. Okay. And now I make an unitary transformation. That means I define a new matrix, which I don't know, I've used already y, but let's call it z as u x. Same thing as in the orthogonal case. Okay. And then this guy here will also remain complex Hermitian, because under unitary transformation it doesn't change its character. And again, you can prove the same object, that is, write down all the measures on the left hand side, dyij product over I less than j. How do I write it? I mean, you understand what I mean. I mean, you write down all the independent entries and take their product and show that this is exactly same as the xij. When I write ij, this means overall independent entries. Okay. So again, the Jacobian is 1. Okay. Do it again for 2 by 2 matrix, exactly same way as before. Okay, and then you generalize it to n by n. Okay. So the statement is that the flat measure, that means if my p is 1, okay, a flat measure in the matrix entry space remains invariant under a similarity transformation. Okay. By flat measure, I mean p is 1. Okay. Similarly, you can do for quaternion matrices, but I'm not. So this is not an obvious statement, but this is something you can prove. Flat measure means p is 1. Possible choices. So there are 2 main categories, okay, here. So the first category is called the independent entries. So that means you choose each element of this matrix, all the independent elements of this matrix, completely independent of each other from some underlying distribution, which could be the same or different. So for example, if it is real symmetric, I could choose something like this. The most general one. I'll explain to you in a minute. Okay. So this means we have remember the matrix. So I have to just think of the first upper diagonal. These are same by symmetry. I don't have to bother about them. Now I can choose each element of these diagonal elements from some functions. So for example, first guy I could choose from f1 of x11. The second guy could be different function, f2 of that element, then f3 of that element, fn of that element. And similarly, for the off diagonal guys, okay, I could choose from any arbitrary function I like, okay, all the off diagonal elements here. So each guy is chosen from independently from some arbitrary distribution. Okay, they need not be the same distribution. Okay, they could be completely different, but they're independent. That means you can factorize this joint probability distribution into like this. Okay, so these matrices, this class of matrices, random matrices, they are in general called Wigner matrices. So for example, just as an example, you see the Gaussian matrix is a special case of this. So in the case of Gaussian matrix, I choose each diagonal guys, each guy is from one independent element. So for example, I could take the Gaussian function for this guy, for each of the diagonal guys, same Gaussian function. And then for the off-diagonal element, actually, I mean, I can choose any different ways, but I mean, suppose I make the choice to do something like this, which is x12 square plus x13 square plus whatever n minus 1 n square. Okay. So Gaussian, of course, factorizes. So you see that each guy I'm choosing Gaussian, and I chose deliberately in this form to so that the variance of the diagonal element is 1, whereas the variance of the off-diagonal elements is just half. Okay. What is the purpose of choosing this? Because if I write this, you can see that I can write down this as e to the power minus half. So here I can just write down xij, xji, or xij square basically. I can write down this as xij square, sum over all ij. So you see, for when there is diagonal element, so you get back this. But when there is off diagonal, x12 square plus x21 square, which gives me just 2 times x12 square. So that's why I chose the variance to be 1. And if I can write this way, you see, this is just nothing but exponential minus half trace of x squared, right? So you remember that trace of two matrices xy is just xij, yji, sum over all ij, right? So if I write it this way, you can see that this guy, so if x and y are same, then trace of x squared is just ij, xij squared. Okay. So therefore, this is half trace x squared. Okay. There is a particular reason for writing this, which will be immediately clear. I'll tell you in a minute. But this is just one choice. You could choose, for example, uniform distribution, exponential distribution, whatever you like. Okay. So all such matrices with independent entries. Okay. So this is the important thing, are called Wigner matrices. So this is one category of matrices that have been studied very well. And the second is what is called rotationally invariant matrices. What do I mean by that? So what I mean by that is that this measure P of x, shorthand notation x for the matrix. So this should be invariant when you make a similarity transformation. That means this function P should be such that P of x is the same as P of, let's say, OX, O inverse. In general, when I write this, I mean, O could be, for real symmetric matrix, O could be just a orthogonal orthogonal matrix. For the Hermitian case, it will be the unitary matrix, and for the quaternion case, this will be symplectic matrix. Okay? So whenever this property holds, sorry, this is not there. Whenever this property holds, that this function is such that you make a rotation in your space of matrices, then this function remains invariant. So such matrices are called rotationally invariant ensembles. Okay? So again, let's take an example. So if I choose P of x to be, let's say, precisely the example that I wrote, minus half trace of x squared. So you see that if I now make an orthogonal transformation to x, okay, x goes to OX, O inverse, the trace, of course, by definition remains invariant, because the trace of this guy x prime will be trace of OX, O inverse, which is the same as trace of x, because you can organize this, O and O inverse is identity, so therefore trace of x. Okay. So under the trace, so when you make the orthogonal transformation, trace of x square also remains invariant. You can just prove it easily. Okay. So I make the rotation, And this traditionally in nuclear physics, for instance, or coming from quantum mechanics, these are very important because you don't expect your matrix, which represents your Hamiltonian of your system, it should not depend on the basis, right? If you change your basis, you choose a different basis, which means you make a similarity transformation, the measure of the Hamiltonian, the energy eigenvalues and all these things should be completely invariant under a rotation, right? So you should definitely use rotationally invariant ensembles for studying physical systems. Okay? When X represents a Hamiltonian of some system, then it should be rotationally invariant. Okay? So there are these two classes of matrices. Okay? So rotationally invariant matrices and the independent entries matrices. And you could choose many other things. So for example, we'll see later that you could choose, for example, this could be any arbitrary function. Let's say if I choose, I don't know, minus some arbitrary function v of this trace of x squared, or for example, I could choose a trace of x squared, then trace of x fourth, for instance, some constant here v. This is also a possible choice, okay, because if I again, so basically trace of any x square, x fourth, any polynomial basically. So that would be a very good choice of examples which are invariant under orthogonal transformations. Okay, so these are generally called matrix models, potential for matrix models as we'll see. But for the moment, let's not. Yeah. Huh? Correlated Gaussian entries. So here I'll just draw these two ensembles if you like. So matrices with real spectrum. So I look at all possible matrices with real spectrum, okay? And as I said, that there are these two classes we studied. So this is the Wigner matrices. And these are the rotationally invariant ensembles. So the choice of this P depends on which ensembles you are talking about. And they overlap. There is only one element in this overlapping region, which is both independent entries as well as rotational invariant. And this is precisely the Gaussian ensemble. So this is a theorem which goes by the name of Porter-Rosenwig theorem. I'm not going to prove this. So Porter and Rosenwig proved that there is only one ensemble and only one possible things in this overlapping region, which is the Gaussian ensemble. Gaussian ensemble, which satisfies both the independent entries as well as the rotational invariant. Because as you saw here, when you make the rotational invariance, it remains. So for example, if I add this trace of x fourth, this is rotational invariant. But if you look at these entries, if you write out the trace x fourth, you will see that the xij's are horribly correlated. You cannot factorize them anymore. Okay? It turns out the Gaussian is the only example. Okay? So you see that Gaussian ensemble therefore plays a very special role, and that's the reason why it has been studied so widely, and because it's both independent entries as well as rotational invariant ensemble. Okay? Yeah. So for independent entries, so all I said is that once we have made a choice of our matrix entries, okay. So from that, I want to go to. So once we make the choice for this, we want to. So this engineer have this dxij. So I want to go to, from this I want to derive the joint distribution of eigenvalues. That's my goal. When can I do it? So for independent entries, that is, if you choose your P of xi's to be independent entries, just like I wrote down Wigner matrices. So the JPDF of eigenvalues, so JPDF short stands for joint probability density function. So this is this object. Okay. So JPDF of eigenvalues in generally difficult. Okay. So for any matrices which belong to this blob here with independent entries, that ensemble of matrices, to calculate the joint distribution of lambda 1, lambda 2, lambda 3, lambda n turns out to be extremely difficult and is not known, except for this guy here, because this belongs to this class for which it's possible to calculate the so for all rotationally invariant ensembles, it's possible to calculate the joint distribution of eigenvalues, okay, which includes, of course, the Gaussian case. So amongst all possible Wigner matrices, only the Gaussian case for which you can actually compute the joint distribution of eigenvalues. But for any other choice, like uniform distribution, exponential distribution, the joint distribution, or even sparse matrices, 1, 0, and things like that, binary matrices, you choose each element to be 1 or 0, for example, okay, and it's not known. Okay. So this is a very, very interesting open problem, okay. So we do not know how to compute the joint distribution of eigenvalues for matrices belong to the Wigner class. N equal to 2 you can calculate, of course, by hand, right? By hand you can do it, okay. But to generalize this to arbitrary n is very difficult. Yeah. Okay. And the point is that once you know this explicitly, this joint distribution, then it's possible to go further to calculate spectral properties, as I said, calculation of observables. This is somewhat analogous to what Kiran was talking about. So if you like, these are the equilibrium problems. I mean, just an analogy. I mean, it's not, these are like equilibrium problems for which you know the Gibbs measure, okay. But these are, problems which have, analog of that would be problems with complicated dynamics, which has a non-trivial stationary state, which is not equilibrium, and then to calculate the stationary state itself is very hard. We don't even know what the stationary distribution of the configurations, okay. So there the measure itself is not known, okay. The measure of the entries is known, but measure of eigenvalues is not known, okay. But so this belongs to a very special class, which is the analog of equilibrium StatMech, where this will be the analog of the Gibbs ensemble, Gibbs measure, okay. And here we'll see that we can calculate also explicitly the joint distribution of eigenvalues, okay. So the next half an hour, that's what I'm trying to try to do. So I want to show you how to calculate the joint distribution of eigenvalues, starting from this joint distribution of entries for rotationally invariant ensembles, okay. In particular, I'll do the Gaussian case, but in the other cases are trivially extendable. Yes? Second point here. So I'm saying that starting from this, you understand the entries, right? Starting from the joint distribution of entries, for example, Gaussian. Now you have to diagonalize the eigenvalues, right? So eigenvalues will also going to be random variables. I want to calculate what is the joint distribution of eigenvalues, okay? And I'm saying that's a difficult problem in general, and it's only possible to do for matrices which belong to the rotational invariant class, which includes Gaussian as a special case. Is that clear? Yeah. So the general idea is that obviously you want to first diagonalize this matrix. So we have seen that this matrix Xij for real symmetric matrix. So let's think of the real symmetric first. So we have seen that the number of independent degrees of freedom is n into n minus 1 over 2, right? You just add up these guys, okay? So how many are there? Huh? Sorry. Ah, you're right. Okay. So what's the idea now? So I'm going to diagonalize this matrix Xij. So when I diagonalize, so that means I want to write down X of so this lambda is the diagonal matrix. These are zeros. And you remember the matrix O, let me just to distinguish from 0. The matrix O is the matrix of the eigenvectors. So its columns are eigenvectors, which are orthonormal. Okay. So when I do this diagonalization, what does it mean? So you are actually making a change of variables. So you had n into n plus 1 degrees of freedom. So again, think of 2 by 2 matrix just as a background. Okay. So x11, x12. Okay. So I had 3 degrees of freedom, okay, which was here. And when I diagonalize it, I'm making a linear transformation. Okay. So I'm going to 3 new, I make a change of variables, okay? So change of variables. And I wrote down explicitly this change of variables in terms of cosine theta and sine theta. So this will be just the orthogonal matrix cosine minus sine, sine cosine, and you just make the transformation. So you are actually going from n 3 degrees of freedom, or in general n into n plus 1 by 2 degrees of freedom, to different degrees of freedom, which are, so I had n, so here I had n into n plus 1 random variables, n into n plus 1 over 2 random variables. I make a change of variable by this relation. So now these are random variables and these are also random variables. Okay? So it's just a change of variable. I'm going from one set of degrees of freedom to another set of degrees of freedom. So how many random variables are here? So here I have n random variables, which are just the eigenvalues. And what about the eigenvectors? How many random variables are here? Can you tell me? How many independent degrees of freedom I have here? Any volunteer? So what do we know about this? So we know that they are orthonormal, meaning that these guys are orthonormal to each other. Each column is perpendicular to the other, right? So their inner product is 0. You also know orthonormal, that means they are, when you square, sum of the squares of this each element is 1. Okay? So how many are there? How many independent entries? How many constraints I have? Very good. So number of constraints is this. Is this clear? Because for example, for the first guy, orthonormality is 1, and then and orthogonality is n minus 1. So the n minus 1 plus 1, which is n. So this guy has associated with it n number of constraints. This guy has n minus 1 number of constraints because I've already taken care of this orthogonality. And this guy has n minus 2, and the last guy has only 1. So when you add them up, you get, these are the total number of constraints, which is n into n plus 1 over 2. And the total number of elements in this matrix is n squared, right? So n squared minus the number of constraints is the number of degrees of freedom. So this is equal to n squared minus n into n plus 1 over 2, which is n into n minus 1 over 2. Okay? Right? Is that right? Yeah. So therefore, what I have is that yeah. So now when I make this change of variable, so I have number of degrees of freedom here is n into n minus 1 over 2, and number of degrees of freedom in this eigenvalue sector is n. So therefore, the total number of degrees of freedom which happens to be the same as n into n plus 1 over 2, right? So you started out with n into n plus 1 over 2 independent entries, and from these entries, I'm diagonalizing. So when I diagonalize, I get n eigenvalues, and I get some number of eigenvectors, but the elements of eigenvectors are not independent. They have some constraints. So total number of degrees of freedom, free degrees of freedom, independent degrees of freedom associated with the eigenvectors, this matrix O, is n into n minus 1 over 2, plus n eigenvalues, n random variables coming from the eigenvalue sector. So when you add them up, you get the same number of degrees of freedom as x. Okay? So this is just a change of variable. So instead of talking about n into n plus 1 over 2 degrees of freedom of the original entry is x, now I'm going to make a change of variable, and I'm going to talk about the eigenvalues as well as the elements of eigenvectors. Okay? And so this is the change of variable. Okay? And once you do this change of variable, you want to know how this measure, probability distribution of the xi's dxi, how is it going to change. So now the idea is to write down this object here into, so under this transformation, okay, so it will go into, in general, probability distribution of the eigenvectors. I'm talking about very general thing, and also joint distribution of eigenvalues as well as the matrix elements of this Oj, okay, independent number of matrices. I'm just making a change of variable from the xi's to this, okay, and here you will have d lambda 1, d lambda n, and then you have this d of Oj, which are the independent. So when I write this Ij notation, I mean only the independent degrees of freedom. Okay. So this p may not be the same capital, the curly p here. Okay. So let's call it I don't know, p twiddle. Okay. So this is the program. Okay. So I'm going from a change of variable from the original xij's to this number of degrees of freedom. I have the right number of degrees of freedom. Here I had n into n plus 1 over 2, and here I have n, and I have n into n minus 1 over 2. So the total is n into n plus 1 over 2. Okay? So I make this, and once I have that, so this is the joint distribution of eigenvalues and eigenvectors, and then finally I want to calculate the marginal of the eigenvalue distribution. Because I don't care about the eigenvectors, okay? So what I want to calculate, the joint distribution of the eigenvalues, which means once I can calculate the joint distribution of the eigenvalues and eigenvectors, okay? So I have to integrate over all the eigenvectors. So that will give me the joint distribution of the eigenvalues. Okay. So there is two-step process. So first is starting from this, under this transformation, you want to find out what is the joint distribution of these eigenvalues and eigenvectors under this change of variable, and then you integrate over the eigenvectors to get the joint distribution of eigenvalues. Okay. And we'll see how it works now. So in order to calculate this, so what you see, of course, what you need is the Jacobian, right, in the change of variable. When you go from x to this change of variables, lambda and O, I need to calculate the Jacobian, which will appear here. So this p, curly p will be there. I have to express the xi's in terms of these lambda's and y's, okay. And then from the measure here, I should get a Jacobian, and so everything will be in this P twiddle. Okay, so let's see how this works. Because you see that I said that x, sorry, I mean, what is the similarity transformation? So x was this O lambda O transpose. That is your change of variable, right? So the Px, only this part, let's look at this part. So this part means P of but I said that for rotational invariant ensembles, this under this transformation, this remains the same. So that means it should be P of lambda. Let's see an example. Suppose I take Gaussian. Okay. So under this change of variable, it becomes e to the power minus half trace of x squared, that means O dagger, O lambda, O dagger, O transpose. So by definition, this is orthogonal matrix, so this is identity. Okay. So this guy is identity here. And this guy, you can take it on this side, because under trace you can actually make a cyclic rotation. So this guy comes here and becomes unity also. So basically what you have is trace of lambda square. Okay, so this is the thing. Okay. So that means this guy is just e to the power minus half summation lambda I square. So this part, you see, does not depend on the eigenvectors. Okay. So it comes out as an overall factor from here, okay, outside. It does not depend on the eigenvectors, okay, as it should not, because it's a similarity transformation. So under similarity transformation, only eigenvalues remain invariant, and only eigenvectors change. So the eigenvalues are completely like this. So this is the advantage of for any rotationally. So for example, this is the. But if I use any other, potential, for example, if I use minus half this v of trace of x, where v is any arbitrary function. So v of z, for example, could be Gaussian, or could be any polynomial like this. Again, you make this rotational transformation, and you see trace is invariant under this rotational thing. So this is under the change of variable. This just becomes v of lambda I summation I equal to 1 to n. Sorry, this is trace of Vx. Okay. And if I choose a Vx to be polynomial like this, then again you can check that it's invariant under similarity transformation, and therefore this guy just becomes V of lambda I. Okay. So that's the advantage of rotational invariant ensembles, that this part of the measure, this P, it depends only on eigenvalues and not on eigenvectors. Okay? And then we have to see how this object here transforms under this change of variable, and we have to calculate the Jacobian. Okay? So then you are done, basically. So I have this. So as I said, there are 3 independent entries, n into n plus 1. So 3 independent entries, which are this x11, x12, x22. So I want to make this orthogonal transformation, this transformation here, x going to dagger. So that means I want to write x as, for 2 by 2 matrices, you know that the orthogonal transformation you can parameterize by this angle theta. So I can just write down cosine theta minus sine theta, cosine theta. Then I have the lambda here, which is diagonal. And then I have Okay. So if I just multiply it out, becomes lambda 1 cos square theta plus lambda 2 sine square theta. This is a 2 by 2 matrix. Okay. So what did we do? So we had 3 independent entries. We made an orthogonal transformation, and from these variables x11, x12, x22, we are going to 3 new variables, which are lambda 1, lambda 2, and this theta. Right? So this is the theta. Remember that in our notation here, this theta represents the eigenvector, if you like, okay? And these are the 2 eigenvalues. So we are going from 3 random variables here to 3 new random variables by this linear transformation. Okay? So therefore, I mean, okay, as I said, for the Gaussian case, for instance, you have so I want to, so as I said, this part transforms trivially into lambda 1 square plus lambda 2 square. It does not involve theta. Okay, you can check that directly by computing this, but it follows obviously from this argument that this is just lambda 1 square plus lambda 2 square. So the only thing is here, this object, so this will be a Jacobian, which should depend on lambda 1, lambda 2 theta, and then d lambda 1, d lambda 2, d theta. So our goal, so this part is done. So our goal now is to compute just this Jacobian. Okay? So this you can do it from here. Okay? So let's see what the Jacobian is. So I have just a linear transformation. So therefore, Jacobian is a matrix 2 by 2. Sorry, 3 by 3. So let me just do it here. 1, 1 is lambda 1 cosine square theta plus lambda 2 sine square theta. x22 okay. So the Jacobian, and same thing, you write down del x11 del lambda 1 del x22 del lambda 1 del x12 del lambda 1, then del x11 del lambda 2 del x22 del lambda 2 del x12 del lambda 2, and finally the third element is del x1 del theta del x22 del theta del x12 del theta. Agreed? So that's the Jacobian. So from this you can work it out what the Jacobian is. And the last guy will be minus 2 sorry, the matrix got deformed, but these are 2 big elements. Okay. So these are 3 by 3 matrix. Okay. So first thing you notice that I can take out lambda 1 minus lambda 2 outside the matrix. I'm just calculating the determinant of this, right? So this means this determinant. So I want to keep this part, right? So just move it here. That's it. So that's the answer. So what you have is the Jacobian is also independent of theta, okay? Which actually is not so surprising if you think about it, and we'll comment on that maybe next day. So the whole point is that everything here, the full change of variable, it only depends on eigenvalues, and it has no explicit dependence on the eigenvector elements, no explicit dependence on theta. It's a flat measure, uniform measure over theta. And so now if you integrate over theta, okay, from 0 to 2 pi, okay, so you get just the joint distribution of eigenvalues for the 2 by 2 matrix. Okay. So this is just taking this and integrating over theta. Okay. So integrate over theta. So that will give you a 2 pi, which you can absorb in the normalization factor, and so basically this is the answer. Okay. So, and this will be true that not just for Gaussian case, but if I take any arbitrary function, potential function of this v of trace of lambda, it will just be, this factor will be just v of trace of, so v of summation v lambda I. So the generalization would be, this will be e to the power minus half summation I 1 to n v lambda I. I did not do the n by n case yet, but when you do the n by n case, which I'll maybe do tomorrow, what we'll see is that this guy, the generalization, all that happens when I go to n by n case is that this thing becomes lambda 1 square plus lambda square plus up to a lambda n square. That is in general the trace of lambda square, or for arbitrary v it just becomes e to the power minus half summation v lambda I going from 1 to n. And this guy here just becomes okay. So this is the generalization to arbitrary n, which I have not done, I have not proved it to you, but I just did it for the 2 by 2 case. So what that means is that for every pair, you get a factor which is lambda 1 minus lambda 2 modulus. Okay? So for example, if you have 3, then for n equal to 3, this factor will be lambda 1 minus lambda 2, lambda 2 minus lambda 3 times lambda 3 minus lambda 1. Okay? So for every pair, you have just one factor which is the absolute value of lambda 1 minus lambda 2. So this is called the van der Monde term. Okay? So I'll prove this tomorrow for general n, because it's quite interesting proof. And this is the real symmetric matrix. Now if you do the Hermitian, complex Hermitian matrix, all that happens is that this guy here just becomes square. Okay? So for real symmetric matrix, so in general you can write this as a beta. Okay, so this beta is called the Dyson index. So beta equal to 1 is the case of real symmetric matrices, and beta equal to 2 corresponds to Hermitian complex matrices. And for quaternion matrices, that is which are invariant under symplectic transformation, this beta happens to be 4. So beta has quantized values, if you like, which is 1, 2, or 4. Okay. And the joint distribution always has a similar looking form, except that this power here, the strength of the van der Monde term, changes from 1, 2, or 4, depending on the 3 ensembles. Okay? And so I'm going to prove this for general n tomorrow, but just to think, just with one comment, I just finished this this lecture. So what you find, as I said, and we'll see that tomorrow that in the general n thing, it's actually, they behave like the charged particles with a Coulomb repulsion, and I'll explain to that in more detail. But basically this is the source, this is this Jacobian term, this van der Monde term, which causes the interaction between the eigenvalues, which, so you say this is the most non-trivial thing out of all this, this thing that comes out is that there's an interaction, effective interaction between the eigenvalues, which causes them to repel each other. And we'll see that this interaction changes the physics completely. If you did not have them, everything will be trivial and everything will be very simple. And it's this interaction term which changes the physics entirely. Okay? Yeah, but first term, you see, if we did not have these, okay, then they are just independent random variables. Okay, you can do anything with independent random variables. It's completely trivial. Okay. If I want to calculate any spectral properties, okay, or calculate density of states, so whatever. For independent random variables, everything is trivial. Okay. It's a strongly interacting case because they are interacting. It's like the Ising model. Okay. If you did not have a coupling term J Si Sj, if you just have e to the power Hi Si, which are completely independent, they are then it's just trivial. You can solve everything. Of course, they are bounded. No, I'll discuss in that detail. I'm not discuss the Coulomb gas yet, okay, which I'll do it in the next lecture. Of course, they are bounded. No, otherwise they won't go into an equilibrium thing. Okay. Basically what happens is that in general, see these eigenvalues. So in this here, they are like sitting in a quadratic potential, confining quadratic potential, and they are repelling each other by this Coulomb force. Okay. And this is what will give rise to finally some droplet of charges. But I want to do that in detail next lecture, so I don't want to comment on that today. So I think I'll end there. Okay. Thank you.